Hi. So next up, we're gonna be looking at counting. So in essence, a lot of the things we've been working with is set theory, and so we're gonna look at how a lot of these things work in sets and how they're kind of coming about. Like how can we work with sets in a better way? So we're gonna break this down into much more simplistic terms. This is Appendix A in the book. Um, I guess I should write these down now that I think about it. So this is Appendix A. And so yeah, so we'll go from there. So first, we're going to talk about one-to-one correspondence. So if I have two different sets, A and B, I want to know when the two sets have the same size. And this is what a one-to-one correspondence really does. It tells us when two sets have the same size. So what is a one-to-one correspondence? You should have seen this in one of your classes. So it's going to be is some map, we'll say phi, from A to B, such that we have two things hold. So every element of A is matched with, so is mapped to a unique element of B, and the same thing for B. So every element of B is matched with a unique element of A. So I'm not going to rewrite that whole thing, but it's basically the same. This just means copy everything from above down. And so that lets us right away. So there's some things we can do with that. First thing is the correspondence rule. And basically what this is saying is if A and B have a one-to-one correspondence between them, between the elements, then we know the size of A is equal to the size of B. So here as a little mini example, let's do green for the mini example. 1, 2, the size of 1, 2 is going to equal the size of A, B, right? I mean, for us, it kind of makes sense, especially with these smaller examples to see what the difference is. But when we start talking about larger and larger sets or infinite sets, this becomes a lot more difficult to figure out when two sets are the same. And so this is why we have to define them in this way. Next definition. When do sets differ from one another? So why does this keep happening? So we say that two sets are disjoint if A intersected with B is empty. That's it. In other words, they don't share anything in common. If they don't share anything in common, they're disjoint. So A intersect B is equal to the empty set. Well, what happens if I have a lot of sets? So if I take the sets A1 through AN. Well, in this case, we're going to say they're mutually disjoint. And what I mean by mutually disjoint is I basically mean that if I take any pair of them, that they're going to be empty. So a lot of times this is also called pairwise disjoint, pairwise disjoint. And that's because these elements come in little pairs, AI intersect AJ. So basically I want each pair to be disjoint, and that's it. So what does that give us? If we have a bunch of sets that are pairwise disjoint, well, now I can just add them up together. So that gives us what's called the addition rule. So the addition rule is basically stating if I have some set A and I split it into some collection of mutually disjoint sets, well, what I have is that the size of A, we're going to make these bigger, that the size of A is equal to the size of A1 plus the size of A2 plus the size of A3, etc. Plus all the way up to the size of AN. And this logically makes sense, right? If I can take my set A and I can put it into different disjoint areas, well, I'm just moving things around, right? So the sum should just be the sum of all the sets. So the next rule is probably one of the harder ones to both explain and to understand. So if you don't get it in the beginning, that's okay. Just come back to this a couple times, and hopefully eventually it'll be there. I don't know what else to say. So basically, in this case, we're actually going to look at a little bit of probability and a little bit of choices. And we're going to sneak peek into some of the techniques used. I think it's in section 7. So it's still a long way out, but we're going to look a little bit into this. So basically, if I have k options or k choices to be made, so I have k different things that I'm going to be working with, and each choice, I can go in nj different directions. So in the jth choice, I have nj different things I can do. So nj options at each choice. Now the question becomes, well, how many options in total do I have? And this is the confusing part. So here, there we go. I'm going to need more space. So we're going to put this here. So we'll have k choices and nj options at choice j. We'll rewrite it. There we go. So let's think about this at the beginning. At the very beginning, so say I start at the very beginning. I have I'm going to do my first choice, and I have n1 different choices, right? So I have n1 different ways I can do. So here we have n1, right? Well, at each one of these choices, once I've made an option, I've chosen an option, each one of these has n2 different ways of happening, right? So each one of these is n2. So basically I have n2 n1 times. So in this case we have so far n1 times n2. And if you think about this, if I keep going, each one of these is going to have n3 options. Each one of these is going to have n4, then n5, then dot, 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 dot. So what this gives us is that the total number of options is, I guess I'll just keep going, is given by n1 times n2 times n3 times n4 all the way up to nk. So we end up having just multiplication of all the different things. And like I said, we'll see this in much more greater detail later on. But it's good to know now how the multiplication rule kind of works. So we'll stop here before we go into some of the more intricate objects that we'll be working with, sequences, orders, permutations, etc. Because now we're going to look at how that example, or I'll talk about this in the next video. So that's it for this video. I'll see you in the next one.